In this video, we want to go over the direct comparison test and limit comparison test for series. So let's start by direct comparison test, or for short DCT. This DCT or direct comparison test says that if you have two series sigma an and sigma bn, and we know that all terms of the sequence an and all terms of the sequence bn are positive, so both of these are greater than 0. And you also know that sigma an is less than bn. It means that a1 is less than b1, a2 is less than b2, a3 is less than b3. Now we can compare sigma an with sigma bn, right? Because if I know all terms of the sequence an are less than all terms of the sequence bn, definitely sigma an should be less than sigma bn. The summation should be less. By direct comparison test, we know that if the sigma bn, which is the greater series, if we know this series converge, then we can conclude that sigma an, which is less than sigma bn, definitely converge as well. And if the smaller series, which is sigma an, diverge, then definitely the bigger one diverge. But we cannot conclude the opposite. It means that if the greater series, which is bn, diverge, we cannot conclude anything about sigma an. We don't know if sigma an converge or diverge. And also, if the smaller series, which is an, converge, we cannot conclude anything about sigma bn. So there are two results for the direct comparison test. If sigma bn converges, then sigma an converges. And the other one, if sigma an diverges, then sigma bn diverges. Another test, it's limit comparison test. Or for short, LCT. We use limit comparison test in the case that we cannot compare sequence of an and sequence of bn. We still know that all terms of an are positive, all terms of bn are positive, but we don't know if an is greater than bn or bn is greater than an. In this case, instead, we go over the limit of an divided by bn when n approaches infinity. We evaluate this limit, and let's suppose that the answer is C. If C is a constant between 0 and positive infinity, then we can conclude by limit comparison test that the behavior of sigma an and sigma bn are the same. So for example, if I know that sigma bn diverge, I can conclude that sigma an diverge, or if sigma an converge, then I can conclude that sigma bn converge. So if I know the behavior of one of them, then I can conclude the behavior of the other one. Now let's see some example together. Question here is summation of 4 minus sine of n over square root of n, and from 1 to positive infinity. We want to evaluate if this series converge or diverge. Let's use the direct comparison test and check if it converge or diverge. By direct comparison test, first of all, I need another series to compare with 4 minus sine of n over square root of n. So let's make that series. In the numerator, you see that 4 minus sine of n, and in the denominator, you see that n to power 1 half. So denominator is n to power 1 half, and numerator is 4 minus sine of n. If instead of 4 minus sine of n here it was just 4, and then denominator was n to power 1 half. So if I didn't have negative sine of n and 4 was the only thing in the numerator, then this series was p series, because when we have a constant divided by n to power p, this is a p series, and we know how to work with p series. uh, if p is greater than 1, or if p is less than a 1. If p is greater than 1, the series converges, and if p is less than 1 or it's equals to 1, then the series diverges. And in this case, it's 1 half. 1 half is less than 1, and it diverges. But this is not a p series. So how can I work? Maybe I can compare it with a p series, n to power 1 half. But instead of 4 in the numerator, we have 4 minus sine of n. So and there is n, and n change from 1 to positive infinity. What we know about the function sine, we know that the output of sine of n, whatever is n, always is between -1 and +1. Now, let's make 4 minus sine of n. And so to make 4 minus sine of n, the first step is to multiply this by negative, and definitely the direction of inequality changed, but still negative sign, it's between -1 and +1. It is obvious. And now we add 4 to all sides of the inequality. So we have 5, 4 minus sine of n, and -1 plus 4, which is +3. So you see that 4 minus sine of n, it's between +3 and +5. So it always is less than 5. It's between 3 and 5. I need 4 minus sine of n divided by n to power 1 half. N to power 1 half, because n starts from 1 and goes to positive infinity, it is a positive constant. Or maybe I cannot say it is a positive constant, but it is a positive. Maybe it's not one constant, but for each n, it is a specific constant positive. So I'm able to divide all sides by n to power 1 half. And now this is the given, and I can compare it with 5 over n to power 1 half, or 3 over n to power 1 half. Okay, this is an, bn, and cn. What we know about these two sequence? If I have series of 3 over n to power 1 half, or sigma 5 to power 5 over n to power 1 half, what we know about this? These two are p series, and um, uh, sigma 3 over n to power 1 half and sigma 5 over n to power 1 half. These are p series, and p here is 1 half, definitely is less than 1, and in this case we know that diverge, right? The series diverge. If the series diverge and I'm using the direct comparison test, if I compare this sequence with this sequence, I know this one diverges, by direct comparison test, I cannot conclude that 4 minus sine n over n to power 1 half diverge. By direct comparison test, I need to compare these two, and now because the smaller series diverge, I can conclude that the bigger one diverge as well. So now we compare our series with sigma 3 over n to power 1 half. So because by p series this one diverged, by using direct comparison test we can conclude that sigma 4 minus sine n over n to power 1 half diverges as well. The next series, it's pretty similar to the previous one. Denominator, instead of n to power 1 half, it's n to power 4. I want to use direct comparison test to check if this series converge or diverge. So again, we are looking for another sequence to compare it with 4 minus sine of n over n to power 4. So let's make that series. We know that sine is between -1 and 1, so negative sine also it's between -1 and +1, and then we add 4 to all sides, then it's between 5 and +3, and we divide all sides by n to power 4, which is a positive constant, and we are allowed to do. Now I know that the given sequence it's between 3 over n to power 4 and 5 over n to power 4. Now when we look at this series 3 over n to power 4 and 5 over n to power 4, both of these are p series, and here p it's equals to 4, it's greater than 1, and we know these two series converge. So which one I need to choose and compare with the given one? 3 over n to power 4 or 5 to n to power 4. We know that when an is less than bn and bn converge, then I can conclude that sigma an converge as well. So I need a sequence and after that a series which is greater than the given series. So if 5 over n to power 4 converge, then I can conclude that sigma 4 minus sine of n over n to power 4 converge. So if I want to use direct comparison test, let's suppose an is sigma 4 minus sine n over n to power 4, then I choose bn as sigma 5 over n to power 4, and because bn sigma b because sigma bn converges by p series test, then I can conclude that sigma an converges as well. By direct comparison test. The next sequence is 1 over n to power 3 natural log of n plus 1, and then we have summation of this sequence. The terms of this sequence when n starts from 3 goes to positive infinity. When you look at 1 over n to power 3, this is a p series, but in the denominator there is another term, natural log of n plus 1. Natural log, it's not like sine or cosine, so we don't know what is the restriction for natural log. Actually, there is not restriction because natural log approaches positive infinity when n goes to infinity. So we cannot compare it with the NP series, right? So how we can approach this problem? So what by direct comparison test or a limit comparison test, which one is useful here? You may think that, okay, I can compare 1 over n to power 3 natural log of n plus 1 with 1 over n to power 3, and maybe one of them is greater than the other one. Because natural log of n plus 1 when it starts from 3, at least it's natural log of 3 plus 1, which is natural log of 4, or 2 times natural log of 2. Natural log of 1 is 0, right? And whatever is after 1, a natural log of that value, for example 1.5, natural log of 2, all of these values are positive. If you remember the graph of natural log, it's this one, and here is 1. So natural log of 1 is 0, and after 1, from 1 to positive infinity, then natural log is positive. But it's positive in some parts, it's less than 1, it's between 0 and 1, and still is positive, right? And not always is greater than 1. So when it's in the denominator, we cannot compare it with 1 over n to power 3. For some n values, natural log of n plus 1 is a positive constant between 0 and 1, and in some case is greater than 1. When it is greater than 1, then we know 1 over n to power 3 natural log is less than 1 over n to power 3, but for the n values that natural log of n plus 1, it's between 0 and 1, then this sequence is greater than 1 over n to power 3. So you see that we cannot compare this sequence directly by direct comparison test with 1 over n to power 3, because for some n values, one of them is greater than the other one, and for the other n values, it's the opposite. So, but both of them are positive. So let's use the limit comparison test. One sequence is 1 over n to power 3, and one series is this one, and the other 3 is 1 over n to power 3. This is a p series, and p here is 3, it's greater than 1, and we know that converge, right? Now, by the limit comparison test, we take the limit of a n divided by bn when n approaches positive infinity. So let's take the limit of 1 over n to power 3 natural log of n plus 1 over 1 over n to power 3 when n approaches infinity. So I can write it as a limit when n approaches infinity, 1 over n to power 3 natural log of n plus 1 multiply with n to power 3 over 1. Now we can cancel n to power 3 or divide numerator and denominator by n to power 3, and when n approaches infinity, natural log of infinity plus 1 is infinity, and plus 1 is infinity, and natural log of infinity, you know that it is infinity. When x approaches infinity, natural log approaches positive infinity. So denominator here is infinity. 1 divided by infinity is 0. So the answer here is 0. As you see, the limit is between 0 and it is less than infinity. So by the limit comparison test, I can conclude that the behavior of the sigma an and sigma bn are the same. what I know about sigma Bn, I know it is a p-series, p greater than 1, converge. So by limit comparison test, we conclude that sigma An converge as well. Why? Because limit of An divided by Bn when n approaches infinity is 0 and it's less than infinity. Okay, that's all about the direct comparison test and limit comparison test. In the next video, I'll go over the root and ratio test for the series. See you in the next video.